Hello.
Oh shit. Hi.
Hello.
Oh.
Hello, everybody.
Hi.
Okay. So it's week 65. Actually, last week we missed something.
Oh, and this
Um,
week we.
no. Last week we were in such a rush.
Mm-hmm.
We forgot to tell people that React 16.13 is released.
Okay. Do you know what's new in?
Yes, I do know what's new. I cannot recall every single detail, but they put up a lot of warnings, deprecation warnings, and warnings here and there.
Okay. Like what kind of things are they deprecating though?
Like a bunch of I'll have a link pointing there.
Okay.
Like a bunch of methods, create factory, like those methods that I never really use, and they're starting to deprecate and they're put up warnings.
Okay. So okay, at least I don't have to read it, I guess.
It's,
Because I probably wouldn't use it.
It's not much going on. That's my summary, but maybe I'm wrong. If I'm wrong, someone please correct me by telling us next week what's important in 16.13. Sunil Pai wrote the release notes.
Okay.
You can alternatively read the release in React repo.
Mm-hmm.
So, anything happened in the RN arena?
So something that happened with Facebook and
Facebook
not
backend?
exactly React Native, but it happens. It's a blog post about the Facebook Messenger. They
That's
titled.
written in RN, right?
Yeah, that was previously written in RN, and they written a blog about it this week on March the 2nd. It's titled Project Lightspeed.
Lightspeed. Wow.
Yeah. So something to take note here is they talked about Facebook Messenger app and a lot of native code, but not React Native code. So I think quite a lot of people think that they are switching, they are ditching React Native, which I don't think so. Yeah, so I think by the project's name, Project Lightspeed, they're actually trying to make the app faster. So when you need to make it faster, I think you need to go to the method. So probably that's why they are not using React Native, because they have identified what exactly they need to be fast, and they are able to spend resource on it. It's like React Native. It's not they are not ditching React Native because it sucks, but they are not using React Native because they need to know. They know that they have the resource, and then they want to be faster.
Oh, so they have a separate project for this.
Yeah.
Okay. I hope Lightspeed is gonna be real lightning fast, not like Zootopia. Have you watched Zootopia, by the way?
No.
There is a character. Is
Oh.
walking the
Oh.
DMV of United States. The
Oh, the sloth.
Yes. If you never watched Zootopia, you should definitely check it out. Right. Okay. So is it gonna affect any of our code base?
For that, probably no. They are probably still gonna have like more changes in the React Native ecosystem. In fact, I think like RN 62 and RC3 is released quite recently. I have not checked it out. Maybe someone can help to understand like what's in there.
Oh look, we have new joiners here. But
Right.
unfortunately, we're a bit late. So
Yeah.
are we introducing new joiners?
I
today?
think.
No.
Can we introduce them? Do you think we have time to introduce them?
Actually, I feel they are probably not prepared for this. So let's
Alright.
keep going.
Yeah.
Yeah. Okay. So let's go to our slides. Is this the correct one? Okay. So we are officially starting. We're week 65 of ceremony to award the limited edition speaker sticker that looks like this, and then the recipient of the sticker will be giving a talk today.
Wow. Wouldn't know.
Yeah, so the detailed information and links can be found in this link. linking to our GitHub issue. And shoutouts to Shopee. Everybody knows where we are at now. And then the whole recording setup is thanks to the generous support by Engineer SG and the technical community. We do have a COC. Basically, don't record our streaming, don't post advertisements in the live chat. Today is a private streaming, so we should not have this problem. You are welcome to invite your friend, but please don't promote anything. And then in our lab chat, which we absolutely love, please don't say mean things to each other, be friendly. Right, okay. Next one. Do you want to take up this one?
So if you want to speak at RK and collect the awesome sticker.
It's designed by our best friend, who should be in the channel also.
Yeah, is our best friend in the channel?
I think so. I think she's in. She's I invited her. She is probably in. She designed this Year of the Mouse. Limited editions.
Alright, so if I want to get that, I have to speak at RK Originals. Like what speaker is gonna do.
We're really bad at this, by the way.
Yeah.
Because it's like sometimes got 4 people line up and saying we want to give a talk, and then we're scheduled to like 4 weeks later, and then for four weeks nobody is speaking. So please consistency, guys. Be like the guy who are speaking today. He has been consistently delivering talk on a quarterly basis, as well as our previous speaker who has been delivering talks every 14 weeks. So please do speak with us if you have something interesting to share. Something going on in the local tech scene. Thanks to COVID, nothing is happening. Not much is happening. Although Junior Dev SG is have code and tell happening next week. If you want to attend physically, I think it's on waitlist now. It's limited to 30 packs, but they will be live streaming at both YouTube and Zoom, like us. In the past week, Talk CSS happened. Our lovely colleague Tanzi had an important statement made, but it's a valid CSS value. Definitely watch that video if you didn't. And then mask go where, full go where, government go where. That's an amazing talk that I had the pleasure of enjoying this personally, not like watching the video, but it was really interesting. It talks about how the website mass go where and full go where, and there are a few more go where ideas are built over the weekend. It was quite entertaining. And then there is this sensor browser API talk by Mandy. It was definitely inspiring, so do check them out. And then GraphQL Hong Kong happened yesterday, I think.
I wonder if Nat is
yeah,
listening in.
Right.
Something about GraphQL.
Does he normally call it to him?
I'm not really sure. Maybe I'll ask him.
Yeah, we should be looking at him. No, yeah, definitely. That's what I'm thinking of. Is Nat's is gonna be excited about this, but I don't know whether he is watching or not. Anyway, all the relevant links are at our GitHub issue. You can find all of them by clicking on them. Okay, today
we have Cryptography for Web Developers by Tiger. I think it's probably going to be only one episode because usually by Tiger we have a series of lectures by
Tiger
Professor.
Has yes. I used to call him Professor, but he called that. But still, he delivers the topics that I am personally the most interested in. Like all the topics, like functional programming, combinators, typography. No, not exactly typography, but font files. These are all the topics that I really want to talk about, but I dare not talk about on the engineering aspect. Because if I deliver a talk on functional programming or anything like that, it would be very blank in a broad idea ways, like, because I'm more into the math part, but he is definitely more into the engineering part. So for engineers, it will be more interesting. Yeah.
So last time he talked about lambdas, and this time he's gonna talk about cryptography. So please welcome Tiger.
No.
Tiger, please.
Okay. So hi everyone. I'm Tiger. Tiger is my mattermost handle. Renamed Jianpo. If you think today's talk is gonna be about cryptocurrency, then you can exit the channel. A little disclaimer: I might cough a little bit during my talk, but don't worry, it's my sensitive throat. I don't have COVID. Okay. First thing first. So the first lesson in cryptography is don't write on crypto. By saying so, I don't mean like those encryption algorithms are invented by no one, but I mean for web developers, most situations that you're in, most problems that you try to solve are already a solved problem in cryptography, and follow the suggestions here. Don't write your own like encryption algorithm that you think so smart. It could possibly have a lot of vulnerabilities. Securities is not a issue to play with. But I also say this because later on I'm going to introduce a lot of abbreviations, a lot of math terms, a lot of like keywords for you to later look up and do research on. But in this talk, I will not explain them in detail because they are too complicated. Okay, so today's contents are going to be firstly we're going to talk about signature and encryption, two of the most major topics in cryptography, and then we'll move on to block cipher basis. Block cipher is a type of encryption algorithms, and then we'll move on to more practical ones like HTTP and TLS 1.3, and then we'll dig deep to AES, GCM, and ECDH in practice. One is encryption, symmetric encryption algorithm. The other is key exchange algorithm. And lastly, if I have time, I would like to talk about cryptography in history, some interesting stories and stuff. So moving on. Those are major topics in cryptography. So signing, generating a signature is like a way to tell recipient of a message that it actually comes from you. So there is only one secret in the whole system, which is private key if it is asymmetric, and the key pair if it's symmetric. By asymmetric and symmetric, I'm referring to the key pair. For asymmetric signatures, you generate you hold on to your a key pair consists of a private key and a public key. Public key is the key you put on the internet, and then for everyone to verify your signature. But the private key is kept by you as a secret. That's the thing you use to generate the signature. But for symmetric signatures, the key pair has two keys and they are identical. They should be held by the receiver and the sender for this message, and they should be both kept as secret. So for best practices, RFC 6979 is the keyword that you want to use and search for asymmetric algorithms. But generally, if you are posting a blog, then probably you want to attach a public key that makes sure that everyone knows that it comes from you. Or symmetric algorithms, which is used in our system, is HMAC over SHA 256. So there are two parts here. SHA 256 or 512 is a hashing algorithm, which basically just feeding a piece of data and then a fixed width hash will come out and representing the content. But HMAC is the algorithm that you apply your key on. So you have a key pair for HMAC, and each party store the key secretly, and you use this key, like the message, if you're sending a message, you use this key to generate a signature over this hash, and then send it over along with the data. And the other party just use the same key to verify this signature against the data to make sure it's integrate. Key pairs are designed for long-term use, but still the best practice would be switch keys once every few months. Okay, now encryption. Sorry. The encryption is the most ancient topic in cryptography. Actually, it's the root of the word. So the goal is to not let unauthorized party to get the message. For example, if you're writing a diary and you don't want other people to see, the encryption is the way to go. So there are some attributes that you should consider when you choose or maybe like in the future design encryption algorithm. Although I don't recommend you to design it. Is for example, the first thing you should consider is those attack methods. Like when you have a encryption algorithm, you should like try those existing attack techniques over your encryption algorithm. They are like replay attack, chosen cipher attack, man in the middle, etc. I will explain one by one later. Second thing you should take care of is that your cipher text should be statistically random. As in, it should look like a gibberish with no statistic features. Like every character, every letter should have the equal chance to appear, and like you couldn't distinguish them between a random text. And then lastly, forward secrecy is something that is brought up during the discussion of TLS 1.3. So it's like let's say you have a series of conversation and you hold on to your keys and use the key to encrypt your messages. If let's say one day a hacker attack your communication and your key is compromised, then all the history of your message history are also compromised, right? But for a system to achieve forward secrecy, it basically just means if the hacker obtained the key for the secret for this conversation, your previous conversation history are still safe. And then for best practices, if you want to encrypt something, there are also two ways: asymmetric approach and symmetric approach. Asymmetric approach is more expensive, of course, and the way to go is elliptic curve-based algorithm called ECC. As you may know, some of you may know that we have a famous RSA algorithm, but it's very hard to get it right in implementation and in practice. And it has some defects, although theoretically it is safe when you do it right. So in TLS 1.3, RSA is removed from the encryption suite. And the best practice here is to simply just avoid asymmetric encryption and go with the approach that TLS use. You use asymmetric key exchange algorithm to get a same encryption key, and then use that encryption key to do symmetric encryption. For example, AES GCM. or simply like just use TLS. I'll explain those terms like is AES, GCM, and ECDH later in a practical coding session. So when you try to use, for example, like Crypto.js, and you try to use AES over your data, like the first time I did it, I got very confused. I thought the encryption is like I give you data and then I give you key. You should give me ciphertext, right? Not exactly. You should also give it like there is another argument in the function called initialize vector, and it has something to do with how encryption is going on for block ciphers. So basically, block cipher is the category of encryption algorithms that process message in many blocks. For example, if let's say the block size is 128 bytes, then your data will be like carved into the portion into portions, and each portion will fit the size. If let's say you have something left that doesn't entirely fit into a block, you will have some padding mechanism to just pad the data. And those padding mechanisms are really like intuitive, simple. And for block ciphers, since you have already divided data into blocks, you use your key, the same key, and over this plain text, and then in multiple like very complicated obfuscated steps, you get your ciphertext. And if you concatenate your ciphertext together, you get your whole ciphertext for your entire message. There is a attack called chosen cipher attack. For example, let's say we encrypt block by block, right? So for each block, it may represent a character in some encoding. For example, let's try like ASCII, and then if you are like designing a game and you're sending a message, encrypted message, telling the server that this player has obtained 1,000 diamonds, and then if you encrypt it in this way, the message, since the same plain text will give you the same ciphertext, it's very easy to identify which part of the encrypted message represents 1,000, right? And then a hacker will, all the hacker need to do is just to inspect the encrypted ciphertext and maybe like send out some, like maybe top up some money and get a specific number of diamonds and replace that part with a bigger number, and you get more diamonds, right? So we need to compensate this, we need a deterministic way to generate different ciphertext for the same block content for the same key, and the way to achieve that is called cipher block chaining encryption. So this is CBC, cipher block chaining mode for AES. That's where initialize vector come in. So the basic idea is to get the previous like blocks ciphertext as a result, as an argument, as a parameter to your next block's encryption. In this way, even though the plain text may be the same for each block, but the ciphertext will be different because it also depends on the previous encryption results. That's why you need initialize vector, and it shouldn't be all zero. Because usually when you use AES with initialize vector, you generate random bytes to feed into it to make sure that you have a random start. And then since the AES is guaranteed to be safe for each block cipher encryption, there is no way for, like, it's safe to provide this initialized vector along with your ciphertext for along with your ciphertext to decryption, and nobody will find out what your key is. And there is no deterministic way to say that this block right here represents 1000, because every time it's different. Okay, so that's how you know what initialized vector does in this scenario, and how you should deal with this initialized vector when you actually implement encryption with AES. But just like I just said, in TLS, AES CBC is also deprecated. What we use now is AES GCM. And the GCM, G represent a mathematical term which I will not talk about here, but C means counter mode. So this is counter mode. This is more performant, and also it has a way to guarantee that the message is, to guarantee the integrity of the message is the G part. But the C part is the performant part. If you look at CBC mode, you need to encrypt the first block to get the second block, right? This way, it's never going to be parallelized. You have multiple CPU cores, but there is only one core that could use for this algorithm, because you need to wait for the previous block's result to encrypt the next block, right? So it's single-threaded. But for the counter mode, since everything happens independently, and there is only a counter, and in this case, this nuance is the initialized vector. So for every encryption, every block, the nuance is the same. It's the random bytes that you feed into it, and there is a counter appended in the back. So in this way, you also guarantee that for the same plain text you get different. Oh, the image is a different is decryption. Sorry about that. It should be the other way around, like ciphertext is in the parameter part. But anyway, this guarantees that it can be run in parallel. You just generate, let's say, 8 counters and then encrypt in one batch, and then you move on to the next batch. Right? So that's how you parallelize it, and it's more performant. Okay. As web developers, we must talk about HTTPS, right? And right now, HTTPS is built on TLS 1.3. This is the latest spec. Just like how HTTP is built over TCP, HTTPS is based on the TLS built over a TCP, and then you transmit HTTP content over TLS. So, only the goal for just like you need to establish a TCP connection before you transmit data, right? You also need to establish a TLS connection to a handshake to establish a secure connection between the client and server. And this handshake has 3 goals. The first goal is to agree on a cipher suit. For example, you use AES CPC or you use AES GCM. And you agree on a master secret, the key that you share in both parties for the symmetric encryption for later content. And then the certificate come in to establish trust between client and server. So it's like when I'm visiting google.com, with this certificate and TLS handshake, I'm pretty sure that this server is the google.com that I'm trying to talk to, not some hacker. Sorry. So a more detailed handshake graph is like this. But since today's talk is going to be focusing on encryption, a simplified version is like this. So here is what happens in a handshake. On the client side, before you establish a connection, you should have a key pair on your end, a public key and a secret key. And you transmit the public key with a client hello message, and it gets to the server, right? And upon receiving this request, server side also generate a key pair. And then it responds with this public key. After this handshake, after this TTL, both parties will have their own private key and the other party's public key. And in this way, like private key 2 plus public key 1, and you get encryption key. The algorithm makes sure that the other party will get the same key for decryption and encryption. And the math is too hard for me, so I'll just use code to explain how this happens. Okay. So today we're going to use AES-GCM as the symmetric encryption algorithm and ECDH algorithm based on elliptic curve for key exchange. And I will not use any library. I'm going to use is web crypto standard. It's a web standard. You can look it up on MDN and all the specs if you want to. Okay. So like I just said, the thing I'm going to achieve here is to generate a secret key on both sides. We have two browser consoles here. One is from Firefox, the other is Chrome. So I'm not cheating right here. Okay, and we're going to use ECDH to perform a key exchange. So we can have the same encryption key on both ends. And then I will transmit, like for one part, we will encrypt a hello world message. And then for the other part, we use the same key to decrypt, to simulate a TLS handshake. Okay. So there are two utilities functions I want to explain to you before I start. One is base 64 to array buffer, the other is array buffer to base 64. So why? Web crypto functions operates on binary data. But if you want to transmit this data over the network, I need to find a representation, and the representation I find today is base 64. Alright, so the two are pretty basic functions. Basically just utilize window.a to b and b to a, and use chart code to encode the string. Alright, let's start. So for the first step, we use this function to create a key pair on both ends. So if I log local key pair, you will have a public key and a private key. And
hold on, we're not presenting this screen to the video. So
can we restart the sharing?
oh, sorry.
wait, right? You need to pick the correct video from your sharing. Yes.
So I stop share.
Yes, you stop sharing and share your current screen.
Okay. But I will switch between screens though.
Then you share the whole screen.
Share this desktop, right?
Yeah.
Yes,
Okay.
I believe so.
How about now?
Let's see. Now can see yours. Yes, can.
Okay. Sorry about that.
Sorry about that.
Live streaming people. Okay, let me explain again. So we need to have a way to transmit data, right? And then the format I choose is base 64. And there are two utility functions I injected in before I start this session, and no other codes, a library I'm going to be using today. So they are all web.crypto, web crypto standard. Look it up on MDN, it's really useful. Okay, so the first thing here is each side, let's call it Alice and Bob. Alice for the black one and Bob for the white one. And the first step is they generate a key pair respectively on each side, and then I need to find a way to pass the public key from Alice to Bob. Okay, so I will convert the public key into a readable form. So I use web.crypto.sato.export key in a raw format. And if you look at public key, it's going to be an array buffer. And then I'm going to encode it into a base64 string. And sorry about that. I executed twice accidentally. Okay, so export key and then encode. Okay, this is the base64 format of the public key. To avoid to simplify the implementation, I'll just copy it over and call it foreign. Sorry, I just copy the key. Foreign public key equals to this string right here. Okay. In Bob's perspective, this is the public key from Alice, and to derive a shared encryption key, I need to use window.crypto.derive key, and it's a relatively sorry about that. Wait, where was I? Yes. Alright. So in this function, I will use derive key function and use the foreign public key and my own private key to get an encryption key right now. Oh, wait. I didn't decode. Sorry, I didn't decode. Yes. Sorry about that. So I need to decode, and now it's array buffer, and then I use import key to convert this binary data into a web crypto key here. Now I get the web crypto key for the public key from Alice, and then here I will use derive key to get the encryption key. Okay, here is the encryption key. We do the same for Bob. So basically, derive a public key from Bob and transmit it over the network to Alice. Alright, and this is a string, and do the same for Alice. Sorry. Alright, and then decode it, and then import it. I'm using raw web API, so bear with me for a while. And then I will use same derive key on Alice side as well. Alright. Now we have an encryption key on both ends. No secret data is transmitted over the network. All we transmit is a public key, and it's safe to expose. How do we make sure the encryption key is the same? Let's encrypt some message. Let's say you have a message called hello world here. And then I encode this hello world into array buffer for the data encryption. Alright, let's look at message to encrypt. Is binary data already. And then let's encrypt this message using the encryption key that I created just now. Oh, IV, yes. It's a good lesson. Yes, I forgot this line. Yes, you okay, so sorry. So this line right here, we need to pay extra notice is because what we have from math.random may not be safe for encryption through cryptography, because we need a relatively more random value than math.random. Okay, there is math terms behind it, and I will not talk about it today. I don't want to scare off those viewers. And then, okay, let's create an IV. Let's look at this IV. It's another binary data. And then I encrypt this message. Okay, hopefully this will work. Alright, great. So let's look at the encrypted message. Oh, it's binary again. Let's encode it. Alright, so there are two things I need to encode. One thing is encrypted message. The other thing is IV. And traditionally, I will append this IV in front of the encoded message, and the decryption, like, so I only transmit one message, and for decoding, or for decryption, we just strip out the IV from the message and then use it for decryption. But here, I'm going to transmit separately. So readable encrypted message and readable IV are here, and I'll copy it over here. Okay, so now Bob has got the IV and the message. Let's decrypt with the key I just generated. Okay, first thing, I should not forget anymore, to decode both the IV and the message. And then is now binary. And then I'll decrypt. Another binary. And then decode this message. And guess what I will see? Readable message, sorry. Hello world. Alright, so just now we simulated a TLS handshake and then encrypted data transmission over the network. Yeah, let's go back to the slides. Yeah. Any questions so far?
There are questions from the others. Technical difficulty. Okay. Do this again. So question, is it necessary to randomize IV well, since it's gonna be exposed anyway?
Yes. So like I just said, this is the deterministic mechanism. If the input, let's say the plain text, the first block of plain text and the initialized IV and the key you're reusing. For example, initialized vector, you're using full zeros. And for JSON data, the first one will be curly bracket. And then you use the same key for different messages. This, you just perform a chosen cipher attack on yourself. So it's like the first character is going to be a curly bracket. And then all your cipher text first block is going to be the same. Right? So in this case, it's easier for the attacker to analyze this information and hopefully get to your key, like at least with less effort. Now you have a plain text, a corresponding ciphertext, and then you do the analyze, and it's easier to figure out. But if you use different, like randomized initialization vector, although the key you still use the same, and the plain text, the first block of plain text is still the same. The encryption result will be different. And there is no way for the attacker to see, oh, this first byte is a curly bracket. This way you don't expose extra information to the attacker. So there are two practices. First, if you're going to use the same initialization vector, you need to use different key for every message. This way you don't even need to pass down initialize vector at all. It could be just a convention that you both sides you just use zeros, right? Or you use different initialization vector and reuse the key. You have to choose one from them. You cannot reuse the key and then use the same initialization vector. Sorry. Yeah.
Any other question from the room? Anything? Okay, let's continue.
Yay. How much time do we have? 10 minutes. Sweet. I can talk about, okay, this part of the talk, I didn't think I can go this far. So the rest are not dry run. Okay, so you have been warned. Okay, I'm going to talk about cryptography in history. The first one is the most ancient encryption, Caesar cipher, and its variants. And then we're going to talk about Enigma, which is an encryption system solution in World War II, with the movie Imitation Game. Have any one of you watched that movie? All right, cool, nice. It's about Alan Turing. You should watch. And then I'll talk about a legal T-shirt of RSA algorithm, the famous asymmetric encryption algorithm that makes everything possible. Okay, first thing, Caesar cipher. So in our ancestors invented this encryption algorithm. It's so simple, so elegant that any uneducated human being can do the encryption. You just need to pick a number and shift every character in your alphabet by the number. For example, if you choose 3, then A become D, and B become E. And then you just compose your message like in this new alphabet. Sorry. So for this cipher, Caesar cipher, it's very vulnerable because it's prone to analysis. If you look at a paragraph or an article encrypted by Caesar cipher, sooner or later you will realize which is this number. For example, you can identify some phrases or some words. For example, if you're writing a document for Shopee, there's definitely going to be a Shopee inside the document, right? And then you just find patterns that looks like Shopee and guess what the offset is, right? If you guess it out, then the ciphertext will be plain text to you, right? Just try out. And if you cannot figure it out, you just try, like, let's say 26 numbers. How hard can it be? 25, sorry. Yeah. But if you have a very, it has some variance. For example, it does not shift very regularly, like just by 3. For example, you can have a dictionary. You can have a random book that you pick from each site's library. For example, I'm Alice, you're Bob. We both like Love in Cholera, Love in Times of Cholera, and then you just pick out that book and say A is equals to page 26, second character, and page character B is page 1 and second character, something like that. And then this way, it's no longer predictable, right? Even if you guess out one character, it's still very hard to guess out the rest, right? So that's how the frequency analysis come into being. So in English, the most frequent word character is E, right? So if you have a very long encrypted message, you just do an analysis over the frequency of each of the character, and the most frequent one, most possibly, will be E. You just brought it in, and guess out the rest. It's kind of like a puzzle game. It's very fun. I like when I was a child, I read a book about cryptography, and the exercise is to decrypt this kind of ciphertext using frequency analysis. Okay, and so this kind of one-to-one character kind of encryption does not work when you have a lot of message to like transmit, right? Unless, let's say, you transmit a sentence, and then for the next sentence you choose a different alphabet, then it's almost very hard, like almost impossible to do analysis over it. And that's actually why this came into being. It makes sure that, but still, this is mechanical in a mechanical way. So it's kind of like a typewriter, and inside you got wheels and I don't know, mechanic stuff. Sorry. And then every time you press a character, there is a light there, here. Like there are 26 characters on the typewriter thing, and there's 26 lights on top. Every time you press down a character, some mechanic system will guarantee that this light will light up. Like for example, you press A and then D light up, and then you just note down D. And then you type messages, and there is a reader beside you that to like note down the ciphertext. But still, it's a deterministic way, as in you have 3 wheels to configure right here. The upper wheel, the middle wheel, the lower wheel. It's kind of like a parameter that you pass into an encryption algorithm. And with the same setup, like the 3 wheels turn to the right position, decryption also happens this way. You just switch the mode from encryption to decryption, flip, and then type down the encrypted message just now, and the plain text will show up above, right? But it's more random than the system underneath is more random than the Caesar cipher, and it makes sure that even if you're typing in a same character, a different character will light up because of the setting. And then so it is used by German army in World War II, and they all come in pairs. Like you have this typewriter, a pair of typewriter, and then you put one in your camp and the other in the army or whatever, the receiver of the command or whatever. But it also comes along with a pair of books, setting books. For example, each book will have, like, say, 1,000 kind of settings. They're all random. But since it's a pair, for each message, you are guaranteed to use the same settings. For example, for the first message, you use the first setting and send out the message, and you cross it off. The other party get the message, set the setting with the, like, refer to the book, look at the first setting, and then decrypt the message, and then cross it off. Right? This way you don't have to transmit your settings anymore, like in any kind of messages. Right? And then even if, let's say, the first day you crack out the settings, the second day it's gone. You have to guess again, all over again. And it's very hard to guess. And then there are multiple iterations. This model I showed here has 3 wheels, and some has 4, and underlying mechanism are like different because it's military somehow. Like, first it's invented as a commercial solution, and then it's obtained by the military. And then we have a decryption, like a tag solution for this. Enigma. Enigma is in German puzzle, and the bomb is, I don't know what it refers to. It's just a bomb, I guess. And the first design was produced at Bletchley Park by Alan Turing. And the first breakthrough was made through a chosen cipher attack. So it's like, I can't remember the details, but it's kind of like, they know this message is gonna contain an address. So this address is the lead to how this encryption mechanism works, because you know the ciphertext and you know the plain text, and then you analyze it. In Bletchley Park, you have chess champions, scholars in language, you have mathematical genius like Alan Turing himself, all kinds of people, like puzzle solvers, and they all just, at first they don't have any clue, right? But suddenly they have this clue. They have a ciphertext and the plain text. And then they just try to figure out how this actually works. And more and more they have more ciphertext that they are sure that is what the corresponding plain text is. And then the more breakthrough they have, and then finally they build up this bomb. But one major contribution is, apart from the geniuses, is that the US Army actually obtained an Enigma machine used by German military in a submarine and its sailing book. And this movie, U-571, is the story of how American American Army knows that this German submarine is sinking, and then they pretend to be the repair submarine, approach it, and obtain the Enigma machine and the sailing book. It's very interesting. It's a bit old, but still a very good movie. And then finally, wow, I never thought I can go this far. Okay, this is, I haven't prepared this, but basically it's a shirt that has 4 lines of Perl programming language that tells the secret of RSA encryption algorithm. And due to some trading laws by US, and some guy just printed out on a t-shirt, and by regulation you shouldn't show any code that has this algorithm inside to a foreigner, right? But you can always wear a t-shirt. And that's how this t-shirt is actually illegal to export and illegal to wear in front of foreigners, but it's actually legal to possess and wear at home. Yeah, thank you. Any questions?
Yes. Are there any questions from the room? Any questions, sir?
There was one where it's about the initialization vector again, but I think we phrased the question wrongly.
Mm-hmm.
So I think the correct phrasing should be why do we need a proper crypto randomizer for IV instead of just a regular randomizer?
Okay, so almost all random number generator in laptop, like in computer, DVD computer, is based on a very long sequence. And since it's a sequence, it's predictable and it's vulnerable, right? Underneath, every time you generate a random number, you're actually using the previous random number as the seed to calculate the next number on the sequence. Right, so it's also a deterministic way. I mean, if you guess out which position you are on this sequence, then it's predictable that which IV that you are going to use in the next encryption, right?
It will be harder to break though than the normal.
Yeah.
Okay, anything else? if not, let's wrap this up. Thank you all for tuning in. We're 7:02 now, and thanks Tiger for delivering this very, very advanced topic from my perspective. What else? So yeah, get back to the pitch to have people speak at Arcade. The next open spot will be March 27th or April 3rd, depending on some specificity. So I will let you know that we do help you prepare for your talk. Your experience delivering your first talk at Arcade is really important to us. So we do dry run and we help you brainstorm your talk idea as well. And then for those of you who are in the room, if you're late, you can still pick up some stickers from my side. And other than that, I think we're good for the night. Alright, bye guys.
Bye.
Bye.